All right, so on the side that says Who Wants to Be a Millionaire, we're going to talk about investing money and gaining interest on it. So one of the primary ways we can use exponential growth is talking about financial accounts. And so we're going to say that you just earned $1,000 bonus at your job and you're going to invest it. You're not going to spend it right away. You're going to invest it. Would you rather receive all the money at the end of the year or half the money now and half the money later if you're going to invest it? Half and half, right? Why? Exactly. So we're going to do half now, half later. So you start earning interest right away. All right, so consider a magical bank that offers you 100% interest. There is no bank that does this. It just makes these examples be a little bit easier to understand. So if you put $1,000 into this account, how much would you have at the end of the year? 2,000. Good. All right, so the rest of this problem, we're doing this 100% interest in a year situation. So instead of being paid 100% interest in one lump sum, let's consider what happens if we get the interest paid out on multiple times through the year in smaller increments. And so let's first talk about if this interest is earned quarterly. So will the amount of interest earned each quarter be the same? So quarter of the year goes by, you add interest onto your $1,000. So the next quarter, is it going to be the same amount of interest or is it going to be more or less? What do you think? It's going to be more because after that interest is added, you have more money. So there's going to be a bigger percentage. So it is not going to be the same each quarter. The amount is growing. Okay, so we're going to fill in this table to see how the amount in the account is changing. And so we're going to have 100% over a year, but divided into 4 quarters. So each quarter is going to be 25%. So let's see how much we're going to have in our account after the first quarter. So we're going to take that $1,000 and we're going to multiply it by something that tax on 25% of $1,000. What would you multiply by? I said that really weird. Not just 1 quarter. If we multiply it by 1 quarter, that's just 250, right? We want to multiply by something that's going to make it the 1250 already. 1.25. So anytime, and you can do this like if you're trying to figure out something. So anytime you want to add a certain percentage, multiply by 1 point and then whatever that percentage is. All right, so that's going to be 1250. All right, so second quarter, we're going to do the same thing, but this time we take 1250 and multiply it by the 1.25. Somebody do that for me, please. 1250 times 1.25. Thank you. Okay, so you guys keep doing it. Keep multiplying by 1.25 until we get to the end of the year, please. So just take the amount we got, multiply it by 1.25, and then do it one more time. All right, so dividing this up, this 100% interest up into doing 25% 4 times a year is actually more beneficial for you, because in the end, it's gonna be $441 more. And it's because that percentage is that interest is making the money grow faster. Okay, so that was quarterly. So let's see what happens if our interest is earned monthly or weekly and daily. So for monthly, how many payouts would that be? 12 payouts. And so to figure out the percent paid each year, we're going to do like what we did with the 25%. We're going to take the 100% and divide it by how many times a year that is. And so for 12 months, it's going to be 8.3%. So the first month, you're going to multiply by 1.083% and then multiply that again and then multiply by that again until you get to the end of the year. So it's the $1,000 multiplied by 1.083. And how many times would you do that? How many times would you multiply by that? 12. Good. All right, so y'all jot that in or put that in your calculator for me, please. All right, did you get $2,603.40? Good. All right, so that's more than quarterly. And so I think you're going to see as we go down that the more times that interest is earned, the more your money is going to be. Now we have to be really careful with significant digits. So I really should have went to more than 2 here because the next 2 I'm going to go, bless you, to 3 significant digits. So on my percent, so 100 divided by 52, because there's 52 weeks in a year, is going to be 1.92%. And then most years, there's 365 days. What's wrong?
Oh, that's example.
Oh, okay. All right, and then that's going to be 0.274%. So make sure that you go to the same number of significant digits there. All right, so you guys take those percentages and that many times per year and figure out those amounts for me, please. I have too many zeros?
So why is there so many zeros? 1.92%. Why is it not just 1.192?
Well, you move that decimal point over 2 places. That would be 19.2%. That'd be great, actually. So, not gonna happen. This isn't even gonna happen. All right. Did you guys get what I got? Which one? Did you raise it to the 52? I got it a couple times. Did you do 1,000? Do you have a 0 right here? You did the same thing that Ryder did. So make sure when you're changing to a percent to a decimal, you move that decimal point 2 places over. All right, so the more often this interest is earned, the more money that you make. All right, any questions on that? Okay, on the back, we're going to talk about some formulas that you're probably pretty familiar with from Algebra 2. Oh, and by the way, it should be 4.3, not 3.3. I didn't change I'm doing my units a little different than Mathematic did. So if you want to change it to 4.3 to keep it straight in your notebook, it's fine. Okay, we're going to talk about two formulas. One we pretty much just used on the other side, which is compound interest. Now we can call this anything we want to. I'm going to call it A for amount. And it's going to be equal to P for principal. And then inside the parentheses, we have 1 plus r to the n raised to the nt. All right, jot that down. You're going to want it tomorrow. All right. You definitely did last year. So I was hoping doing that table where we actually did the division that it'll help you remember this part of it. Okay. All right, so P stands for principal, and it is the initial amount invested. And then R is the interest rate as a decimal. All right, N is the number of compoundings per year. Bless you. And then T is the number of years. One thing I used to do with my Algebra 2 when they were just learning about E, which is Euler's number, he's the red guy on the wall, is that I would take the number of times per year and I would raise it to I would have it be like every second of every day in a year. And what happens, or the closer and closer, or the bigger and bigger the number of times per year gets, then that rate gets closer and closer to E. And E is 2.718. So anyway, that's where E came from. And we use E on continuously compounded interest. So the number of times the interest is compounded is approaching infinity. Like it happens so often you can't even see it. Like it's constantly happening. And this formula is easier to remember. So it's just A equals P, the base is E, and it's raised to the RT. And E is Euler's number, which is approximately 2.718. It keeps going like pi doesn't repeat a pattern. You don't need to really know what E is. It's helpful, but your calculator has 2 E's on it that you can use anytime you need to know what E is. Okay, so let's answer some questions. So for example 1, each scenario represents $400 invested at 5% over a course of 2 years. For each scenario, determine if the interest was compounded annually, biannually, quarterly, monthly, or continuously. So annually would be once a year. Biannually is twice. Quarterly, obviously, is fourth. We already talked about that. Monthly is also, we already talked about, is 12. And continuously and is approaching infinity. So it's just always happening. What do you guys say about A? How many times did the interest accrue in 2 years? I don't think so. It started here. 1, 2, 3, 4, 5, 6, 7, 8. So 8 times in 2 years means 4 times in 1 year. So this is going to be quarterly. What do you guys think about B? Yes. Okay. Let's look at 2. So it'd be great if you guys can do this for your kids. I wish someone would have done this for me. But on the day of a child's birth, a deposit of $25,000 is made in a trust fund that pays 8.75% interest. Determine the balance in this account on the child's 25th birthday. If interest is compounded weekly, monthly, continuously. All right, so weekly is going to be 52 times a year, every week. P is going to be that $25,000. And then R is going to be 0.0875. And for weekly, we're going to put it into this purple formula, the compound interest formula. So it's going to be 25,000. And then parentheses 1 plus 0.0875 divided by 52 raised to the 52 times the number of years is 25. All right, you guys type that in. It's got a lot going on. Type that in and see what you get. I want to be this child. I was going to say, that's not what I got. Did you guys get $222,413.32? It's not too bad for just being born. My poor kids, they got to make their own money. All right, so let's look at monthly. You think monthly is going to be more or less? It's going to be less. Should be. So everything's going to be the same except the 52s are going to turn into 12s. So that made about $1,000 difference. A little bit more than $1,000. Around $1,300 difference. All right, and then the last way we're going to do it is continuously compounded. All right, so it's just going to be 25,000 times E raised to the 0.0875 times 25. So you need to find E. It's second and then ln right beside the 4. That goes ahead and raises it to a power for you. The other E is second and then the divided symbol. Okay. So we already knew that was going to be the biggest amount.
I thought it would be like significantly bigger. If you got compounded 24/7.
Yeah. Well, no, it doesn't make that big of a difference, I guess, in the end.
You get like another 500.
What really makes a huge difference is the interest rate. So if you can get a really good interest rate, then that's good. Also, think about accumulating debt. The interest rate really does make a huge difference in accumulating debt for things that you borrow. Okay, so the last question is about bacteria. So things in nature, like bacteria, grow exponentially with E as the base. And that's why E is called the natural log. So bacteria is one of those things that grows. We're going to use the continuous exponential growth model for it. And the rate is going to be 8.1%. So we're going to make sure we use that as a decimal. And so if there are 1,800 bacteria at time 0, or the initial amount, that's going to be P. We're going to write an equation that gives the number of bacteria after T hours. So I'm going to start with A equals, I'm going to put the initial amount of bacteria, E raised to the 0.081 T. All right, so that's what you do when you're just writing a model or writing an equation to model the situation. And then B wants us to use that model by plugging 6 in for T. So find the amount of bacteria after 6 hours. So I'm going to round to the nearest bacteria. Typically on money, you round to the nearest cent. On things like bacteria or bunnies or whatever, you round to the whole number. Okay, so what questions do you guys have about exponential growth applications?